Hello and welcome to Data Science in Industry vlog. Today I would like to tell you about predictive maintenance. This is the maintenance strategy that is based on predicting failures. We are taking our service action before the failure. So we need to predict when the failure will happen, what is the risk of a failure. This is a hot topic right now in the industry 4.0. We are implementing such predictive maintenance platforms for our customers. Many customers would like to have such predictive maintenance platforms in their plants and their factories. I would like to stress the fact that such projects should be reasonable. My advice is to start with a POC, with a selection of some devices, some problematic devices. So we should focus on devices that are problematic, that are related with some failures that are happening from time to time. Moreover, those failures must be costly. Should be costly. So we should choose such devices that have failures from time to time, and those devices and those failures cost us significant amount of money. Then we, as a plant owners, we can consider purchasing such a predictive maintenance platforms. We have such situation. Moreover, we should also focus on devices that and particular failures of those devices characterized by the fact that if we are able to detect or predict such a failure, we have enough time to do some action. So we don't want to say that, we detect the failure, game over, you can stop your process. Right? So what is the reason for having such a predictive maintenance platform? We should focus on failures for which we can say, hey, there is a high risk of a failure, you can do something, you can order new parts, you can lower the load of this equipment, you can switch this pump to another one, switch this cool mill to another one, switch this compressor to the one that is not operating right now. All right, so we have time to make the action. And then having such a platform is a very reasonable thing. Okay, so if we know what are the devices that we can consider to be covered by such a platform, that is reasonable to cover them by such a platform, then we can go to slides and discuss this topic in more details. Maybe one more remark. Of course, there are devices that are not related with the high number of failures. Maybe in their history we don't have any failure of such a device like turbine, gas or steam turbine or a transformer, right? But when the failure happens, the cost is really, really high. So of course we should also cover such devices in our predictive maintenance platform. In this case, we will not be able to find the historical data associated with the failure. But of course, there are norms. We have a data that represents normal behavior of such a device, so we can use it to model normal behavior. However, if I can recommend you something, for the POC project, it's better to start with a device that has some failures in the history, in the digital history. So we have a data from a month ago, 1 year ago, 2 years ago, when the failure actually happened. Because thanks to this, during the POC project, we can check if we are able to detect such a failure, right, based on historical data. So this could be the proof that the algorithm can be useful. Okay, so now we can really switch to slides. The maintenance strategy can be divided into reactive and proactive. The reactive approach is failure-based. So we are doing the service action after the real failure, right? So usually it's too late. We are trying to fix the real failure that actually happened. So unfortunately, this is my default approach in my house. So I'm waiting for the failure, and then I'm fixing the device. The failure of the washing machine, the failure of a lamp, etc., vacuum cleaner, etc., etc. And by the way, I'm talking to my wife. If I say I will fix it, I will fix it. And you don't have to remind me about fixing this device every year. Okay, so the proactive approach is probably better. For sure it's better, especially if we are considering the plant or the factory. The proactive approach can be divided into preventive and predictive. The preventive approach is age-based, let's say, right? So every period of time we are doing the service action. So we have a device and we know that we have to do the service and maintenance action every 3 months, right? Or every year to prevent the failures. We are replacing parts, checking the oil, etc., etc. Every year we are taking our car to the mechanics to check its state, to replace the oil, etc., etc. But the new approach is the predictive maintenance. So this is the condition-based approach. So in this approach, we try to do the service and maintenance action right on time, when the device needed, when there is a risk of a failure, when we are predicting that the failure may happen in the nearest future. And we will talk about this approach today. Here you can see the evolution of asset management, of the maintenance strategies. So the reactive strategy was the first one. Then we have this preventive approach, which is more or less a standard in the industry, to perform the maintenance actions regularly, to reduce the probability of the failure. Now we have those new predictive maintenance platforms, the new predictive maintenance algorithms that tries to predict the failure, and based on such predictions, based on such estimations, we can take the maintenance actions before the equipment failure. And we can extend this approach into the prescriptive maintenance. So in this case, we are not only informing that there is a risk of a failure, but also we are suggesting what steps need to be taken, what to do to, first of all, avoid the failure, mitigate the risk of the failure, or at least what to do to lower the negative impact of the failure. We can just recommend such an actions, right? But we can also connect the algorithm that predicts the failures with the algorithm that optimizes the plant. And if the algorithm that optimizes the plant automatically using AI, for instance, if it controls a particular device, so it sends the decisions to the control system that have an effect on a particular device. Let's say it decides about the load of this device. If we know that there is a high risk of a failure, we can send this information directly to this optimizer in order to lower the load of this device, switch this device to another one, so the estimated costs and the probability of those costs of this failure is a part of the quality indicator of the mathematical formulations of our optimization goals. So we want to minimize costs, maximize efficiency, minimize energy consumptions, right? And minimize costs related with failures. So this part related with costs of a failure is taken into consideration while proposing the optimal operation of a factory or of a plant. So we are finding a compromise between the high utilization of a highly efficient device that help us to reduce costs and the risk of a failure of such a device and the costs related with this failure. I think this is those projects are the most interesting. We had some projects like this, and this is, I think, the future, because you can see really the value of such a predictive maintenance approach, especially when you can combine it with the value that comes from the optimization algorithm. Okay, so in the predictive maintenance, our goal is to predict the failure, so detect the process state that leads to the failure. This is the holy grail. We would like to detect the state of the process or of the device that is associated with the upcoming failure. Of course, detecting a failure when it actually happened is also a good thing, right? Because especially if we can take some action to minimize the impact of this failure. But we would like to detect the early symptoms, the state of the process that is associated with the risk of a failure in the nearest future. Such a process state is usually associated with abnormal operation of a device. We was talking about abnormal operation in the last video. Such an abnormal operation is related with anomaly. So anomaly detection, that approach to the algorithms that detects anomalies, usually are part of the failure prediction, right? Usually are part of the predictive maintenance algorithms. So I say that the failure is the anomaly that we can name it. We know what are the what causes such a failure. We know what are the results of such a failure. Then we can, if we know those things, we can name the anomaly a failure, right? The abnormal operation, it's not always a failure. Of course, it might be related with the early symptoms of a malfunction. It can be related with the state that leads to the failure, but also it can be related with the condition of reduced efficiency. And I think it's also worth to detect such states. It's not it's not a failure, but we would like to detect that that the device operates with reduced efficiency, because we can do the action, we can take the action that will help to improve this efficiency. For instance, what are such states of decreased efficiency? Diluting of the coal in the mill, the contamination of heat exchangers, right? We can try to, in case of such heat exchangers, we can try to clean it. In power plants, in power boilers, there are dedicated equipment. There is a dedicated equipment that blows the air on such heat exchangers and improves the heat transfer, the heat flux. What is the general idea behind algorithms that predict failures? First of all, we have a control system, a distributed control system or set of PLC controllers, and we can get the data from these control systems. So we have those signals that correspond, that represents the temperatures, flows, device states, process configuration, etc., etc. Based, of course, we have to do many times we have to do additional calculations based on those signals in order to, calculate the humidity, do the signal filtration, do the signal aggregation, estimate stresses, etc., etc. Then we can use those raw and transform signals to calculate the diagnostic signals, and use those diagnostic signals to infer about the risk of a failure. So what kind of diagnostic signals we can have? Well, we can see that temperature is too high, then the difference between reality and our digital twin is too high, etc., etc. Right? And the set of those diagnostic signals can be used to estimate the risk of a failure. Those diagnostic signals can be based on the analysis of a single signal, right? So we can check if the signal value goes beyond the acceptable range, if it's higher than the maximum limit or lower than minimum limit. Usually the alarm module in distributed control systems operates based on the comparison of the process value and some ranges. If the value is beyond the acceptable range, then the alarm is raised. But of course, this is a very simple approach. We would like to detect some slight difference in process behavior, very early symptoms of a failure. So probably such approach would not be enough. We can also check the derivative of a signal value if it goes beyond the acceptable range. So the speed of changes, right? The rate of changes. If the rate of changes, if the signal is flat, and normally it was, moving, then it means that something is strange, right? Or a signal or the value of this parameter increases with a very high rate, higher than in normal operation. This also could be a diagnostic signal. Or the variance, right? So I already mentioned about this. So if the variance or a measure of variability differs from the norm, from the normal behavior, like for example the signal is flat, then it could be a diagnostic signal. Those are very simple approaches. Maybe a better approach is to use the statistic analysis of groups of signals, right? So we can check if the linear correlation between signals are not changed in comparison with normal behavior. Of course, usually we have a dynamic system, so the technological process is related with some dynamics, some transport delays, some inertia. So while calculating such correlations, we should take into account shifting signals in time, right? So we should capture this dynamic. We can calculate the derivative, the linear correlation between derivatives of signals, etc., etc. So this approach is based on such an assumption that, if the temperature was this and the flow was this, the pressure usually was somewhere here, not here, right? So we try to find the links between those signals, the relation between those signals. But of course, the best formulation of those relations are predictive models, right? So in this approach, we can focus on particular parameters of a technological process, and we try to build models of such parameters based on industrial process inputs. So the model captures all those relations, and if there is a difference between the model output and measured value of a particular parameter, then such a difference can be a diagnostic signal. Right? So this is the digital twin approach. We can use very simple models, static or dynamic, depending if we have to consider dynamics or we can skip it. So every time we had to think about this. We can use linear or nonlinear models, right? We can use even deep neural networks. We had such projects where we used deep neural networks to create those predictive models that are used in calculating those differences. All right. And of course, the final decision about risk of a failure can be based on the mix of those three approaches, on a digital twin, but also on some statistical analysis of particular signals. I already talked about this picture in the anomaly video, but I think we should discuss this once again in the context of failures. Right, so we can have three different cases. We can have historical failures in our data. So we have a data from 3 years, and there are some failures, like about 20, 30 failures in the historical data. If we have such a case, then we can try to create a supervised algorithm, a classifier that will predict the failure, calculate the risk, the probability of a failure. The set will be unbalanced, of course, but we can use different methods to handle this. But this is a very rare situation. Usually the failures is not something that happen many times, right? Usually the process, the plants, factories operates without the failure for majority of time. So the typical situation is this one, where we have a historical data. Majority of this data comes from the normal operation, and we can use this data to create the model of normal operation, this digital twin, where we can select some parameters, some crucial parameters that can help us to detect a particular type of a failure. I call them traps for a particular type of a failure. If this, I don't know, it's a failure related with some oil leakages, so we can take the parameters that represents the oil flow, oil temperature, etc., right? And so every time we have to think about which parameter to choose to detect a particular type of a failure. This is a crucial step in creation of such an algorithm. Then we can create a model of normal behavior and compare the output of this model with sensor values. If there is a difference, we can estimate the risk of a failure based on this difference. And there are also cases where, in fact, we don't have any failures in the history. We even not able to say what kind of failures are crucial. Then we can apply just anomaly detection methods to at least inform the operator that, well, this particular case, this particular parameter looks suspicious. We don't know if it's a failure or not, but please take a closer look to this parameter, because it looks strange. It differs from the norm, given the context, given the process operating point, the equipment load, etc., etc. So now let's talk about the inference on abnormal operating condition. Like I said, the prediction of the failure, the prediction of the risk of a failure is based on the calculation, is based on those diagnostic signals. We can have very different approaches. We can use some expert rules to infer about the risk of a failure. If the temperature is higher, if the difference between normal and measured temperature is high, or the flow is lower than expected by some value, then we can say that there is a risk of a failure. Sometimes the norm can really help us, some standards for particular devices. There are such documents and we can use them. If we have many, let's say, experts on the plant, we can use the fuzzy inference. Sometimes it's hard to define the strict rules, but we can talk with operators, with dispatchers, and I can say that we should report the high risk of a failure when the difference between the current measurement and the model output will be large, while the variance of the measurement will be low. Right? Those are those fuzzy. This is the fuzzy approach, so they do not specify the exact number the threshold. They say that something is large while other things are low. And of course, we can define fuzzy sets that defines what does it mean that the parameter has a large value or the parameter has a low value. Or we can use the nonlinear or linear classifier in order to inference about the risk of a failure. But in this case, we need to have enough samples, enough cases on which we can train the classifier. So rather, we don't have such comfort of using this approach. Rather, we should focus on some expert rules, because a lack of samples in the historical data. And please remember that the proper definition of those thresholds, proper definition of those detection rules is crucial. If we will define the detection mechanism too broadly, right, we will relatively frequently inform the operator about the abnormal operating conditions. So in most of cases, it would not be connected with real malfunction, right? So the operators, the dispatchers, the maintenance teams will close this, will stop our algorithm, because it will give too many false positive alarms. If we will define those rules too restrictive, there is a risk that we will not detect all the failures, all the malfunctions, or state that leads to the failure. Right? So there will be a real failure, and our algorithm will say, the risk is not so high. So it is important to find the compromise, the balance, the thresholds, the rules that will find most of failures while not generating too many false positives. Probably you know the concept of the confusion matrix, right? Please take a look here. We can have 4 different cases, right? Here is the real failure, and here are our predictions. We can have the failure in reality, and we can predict that there will be a failure. So this is a true positive, right? A win situation. We could predict the real failure. For most of time, there are no failures, and if our algorithm also reports there is no risk of a failure, then it's also a win situation. We call such cases true negatives. But we can also have 2 types of errors, right? So if there is a real failure, we can say, no, there is no risk of a failure. This is a false negative, right? On the other hand, there might be no real failure there might be no failure in reality, but we can say, hey, take a look, there is a very high risk of a failure, and this is a false positive. I mentioned about false positives while discussing this too broadly defined detection mechanism. So based on this, we can calculate F1 score or recall and precision. Those measures help us to assess our algorithm. Because, we can take the extreme case and we can say that our algorithm looks like this. Every time, at every timestamp, report the high risk of a failure, right? So it will raise the alarm all the time. With such an algorithm, we will detect all the failures. We will predict all the failures, great, right? But such an algorithm is useless. You understand? Nobody will trust it. Operators, they will just close it and do their business, do their tasks without looking at the algorithm. So we have to find this compromise. And on the end, I would like to once again discuss this case with coal mills. I know I was discussing this case in the last video, but here I would like to go a bit deeper. Of course, it's only one case related with failure prediction. We are predicting failures of transformers, pumps, and other devices. But I have nice slides for this case. It was one of the first projects with predictive maintenance, and that is why I would like to go a bit deeper right now with this topic. I promise it's the last time I'm discussing the coal mill. So here our task was to detect failures related with the coal mill, with a device that grinds the coal using such bowls. So the coal is fed to the coal mill. Also the air is fed to the coal mill. Then the coal is grinded, and the coal air mixture is coming out of the coal mill into the combustion chamber. This coal air mixture has some temperature, some flow. There is some pressure. We have many parameters that describes this coal mill, the airflow, the feeder speed, the feeder with the coal, right? The current consumed by the coal mill engine, the current consumed by the fan engine, differential pressure, temperature of the primary air that comes to the coal mill, and the flow of this air, etc., etc. So there are a lot of parameters. Now the question is which one to choose to detect failures. So of course, first of all, we need to know what kind of failures can be related with such a coal mill. I think two most frequent failures are coal overload. So we have too much coal mill overload, right? So we have too much coal in the mill. The coal mill is not able to grind it. And another failure is that there is no coal in the coal mill. The feeder is moving, but the coal is not entering the coal mill. Maybe there is some blockage or lack of coal. Who knows? So we should be able to create an algorithm that detects at least those two failures. The question is which parameter to choose. Which parameter can be a good trap for such failure? So, in other words, if there is a failure, which parameter shows us this failure? We identify two such parameters: the current consumed by the coal mill engine and the outlet temperature of this coal air mixture. Right? Because you see, if there is too much coal in the mill, the mill is overloaded, then we would have higher current consumption, right? If there is no coal, or the amount of coal in the coal mill is low, then the current consumed by the coal mill will be lower. Of course, one can say that why not to just set some alarms, set some limits, minimum and maximum limit, and raise the alarm if the current will be higher than the maximum limit or lower than the minimum limit. But the problem is that those current differences are let's say small. If the mill is overloaded, the current consumed by the coal mill is higher, but still is within the acceptable range, right? At least for a while. The same with lack of coal. The current consumed by the coal mill decreases, but for a long time is in acceptable ranges. The same with the outlet temperature. The coal is definitely colder than the air that is supplied to the coal mill. So if the temperature will start to decrease, the temperature of this coal-air mixture will start to decrease, it means that we have a higher proportion of coal to air, right? Or cold core to hot air. So on the other hand, if the temperature will start to increase, then it means that there is less coal in the coal mill and more air in proportion to the coal, so the temperature is rising. And that is why we made two models: the model of the current consumed by the coal mill and the model of the temperature. We used deep neural networks to do this. Here is the result. In normal operation, the red signal is the model output, while the blue signal is current consumed by the mill. As you can see, it's associated with a high noise. And here we can see the coal feeder blocking failure. It was detected half an hour before the operator's reaction. Here we can see that the current consumed by the coal mill is decreasing, but still it's in acceptable range, right? 21 amperes, it's still something, okay. But in comparison with our estimation of normal consumption of normal current consumption, it's essentially lower. This estimation takes into account, current feeder speeds, the airflow, temperatures of the air, etc., etc. Many parameters. I think I don't remember exactly, but it was like few hundred parameters on the input, because we also considered some transformations. We also estimated coal humidity. We also take into consideration values shifted in time in order to capture process dynamics. And on the end of the day, you have to present the operator or the maintenance team the result, the information about the anomaly, about the failure. So you will have to create some simple graphical user interface within the control system, so the operator can open because the operator normally, they use the SCADA system or distributed control system in order to control the process, to observe and control the process. So within this system, you have to add a new operator graphic where the outcomes of the algorithm are presented. Like, for example, here there is a risk of the mill overload, so the anomaly is detected. All those signals are in normal ranges, but still we are detecting the mill overload. Because the sensor value associated with the mill motor current is higher than the model. This was done in one of the Polish power plants. You can read more about this in the book Thermal Power Plants, and we have a chapter about detection of malfunctions and abnormal working conditions of a cool mill. But in another plant, we combine this approach with the optimization system. So the optimizer, the artificial immunous system that autonomously controls the combustion process, also uses cool feeders, in order to minimize emissions of NOx, minimize emissions of CO, maximize the efficiency of the process. It uses the six coal feeders to change the distribution of fuel to the combustion chamber. But when we detect, it's also our optimizer, so it was easy for us to combine it with such an algorithm that detects problems or risks of a failure associated with the coal mills. If such a risk is detected, the signal is sent to the optimizer to reduce the load of this coal mill, right? And of course, automatically the optimizer has to increase the load of all other mills. So this is this step forward to prescriptive maintenance. It was a very, very interesting project. Here is another example of a project. Here we try to predict failures in the long term. So here it was rather a short term, right? We had minutes to the failure, minutes for taking the action. But we also have projects where the time horizon is much longer. We have months. It covers months or years. In such cases, the time factor has to be taken into consideration. So in this project, our goal was to estimate the risk of a failure of a pipe in a district heating network. It was in Toruń. So this Toruń is one of the Polish cities. So the team in Toruń, they needed in order to optimize their maintenance strategy, because during the summertime some of the pipes can be replaced. So there is some budget for replacing old pipes, but rather pipes associated with a high risk of a failure, right? And the question is which pipe to replace, which pipes are associated with a high risk of a failure. And we took many parameters of those pipes, diameters, material, when they were built, if they are under or overground, what is the type of isolation, etc., etc. The number of failures in a history, right? And of course, the age. Based on those parameters, taking into account historical failures, we was able to create an algorithm that predicts the risk of a failure. And of course, the time, the age, is important, very important factor. It's not the only factor that should be taken into consideration. Not always the oldest pipes are associated with the highest risk of a failure, but it's an important factor. So in such case, you should, if you are developing such an algorithm, you should take into consideration this this time factor, the age of equipment. And this is the last slide. Maybe on the end, I will just say that the same as for anomaly detection, we should also consider the fact that the technological process, our plant, our factory, our devices, its characteristics are changing over time. So we have to take this into consideration. Also, while calculating the budget of such a project, the maintenance of the models used for failure prediction is an important part of the project budget. Such maintenance can be done manually based on the most recent historical data, or we can try to apply some mechanisms that helps us to adapt our models to the current process situation, to the current process characteristics. All right, so thank you for your attention. I wish you a great day, and bye-bye.